今天我们非常荣幸邀请到中研院数学所的何正卫研究员。那正卫的研究领域包含 random matrix theory 还有 free probability theory。那今天他演讲的主题是 heat flow on random polynomials。然后让我们掌声欢迎他。
All right. Thank you for the introduction. Thank you for the invitation. It's my pleasure to give a talk here. So today I'm going to tell you heat flow on random polynomials. So let me start by random polynomials. So as the name of random polynomials suggests, random polynomials are polynomials selected at random. Okay? And in order to be able to perform some analysis on the random polynomials, we usually assume the coefficients are independent. Okay? So it's just like the independence that you learned in the probability class. It's like when you draw cards from a deck of 52 cards with replacements. It's like every time you draw a card, you do not really distinguish the draws. Okay? And well, with a polynomial, what we are interested in is the distribution of the roots. So it looks like a bit weird. Maybe I just use the keyboard to control. Okay, so let me tell you some applications of random polynomials. So it's usually used in physics. One thing that physicists use to understand using random polynomials is quantum chaotic dynamics. And random polynomials, or I mean the roots of random polynomials, are used to model the positions of a two-dimensional gas of particles with repulsive interactions. It is also used to model the positions of vortexes appeared in a two-dimensional rotating ideal Bose gas. So ideal Bose gas is the quantum mechanics analog of classical ideal gas. Okay. So let me give you some example. So the first example is actually a classical one. It's called the Weyl polynomial. I kind of rescale that so the roots are actually inside the unit disk. So the Weyl polynomial is given by the sum of k from 0 to n of ck square root n c raised to the power k divided by square root k factorial, where ck here are ideal random variables. That means independent, identically distributed. So if you don't know what that means, you just regard all of these ck are kind of the same. Well, same is not quite accurate, but I mean you cannot really distinguish these random variables. They are independent, and the distribution is the same. And the only technical assumption that I put on ck is that they have finite log moment. Okay, so with this example of a Weyl polynomial, the limiting root distribution of the random polynomial is the uniform distribution on the unit disk. So here I'm showing a degree 1000 Weyl polynomial. So you can see that the roots are approximately uniform in the unit disk. Of course, there are some outliers, but they are pretty uniform in the unit disk. So the next example has a more simple looking form. It's just sum of ck times c to the k. Okay. Again, ck are ideal random variables with finite log moment. In this case, the limiting log distribution is uniform on the unit circle. And again, you see that the roots are not really exactly on the unit circle, but the limiting root distribution is on the unit circle. You can see that they are very close, and there are just a few outliers. Okay?
Sorry, the limit is n goes to infinity?
Sorry? Yes.
What is the limit?
Yeah. The limit here, I mean, I fix an n, I look at the n roots, and then I take n to infinity, and I try to look at the distribution of the roots. So now let me tell you the main question of today after telling you two examples of random polynomials.
No, I have a question. Why the two pictures are so distinct?
Sorry?
Student distribution 一个是supported on the boundary, the other one is inside the disk. What's the difference?
The difference comes from the deterministic coefficients. Here is square root n to the power k over square root k factorial. And the other one is constant 1. And later of the talk, I will tell you there is actually an explicit formula determining the limiting root distribution. Yeah, so the way to compute the limiting root distribution, you always just look at the coefficients. All right, let me tell you the main question of today, and then I will go ahead and give you some example and tell you how we solve this problem. So the main question of today is that, well, I have a random polynomial or a polynomial. I'm interested in the zeros, and I want to study how the zeros of a polynomial evolve under the application of the heat operator exponential minus t over 2n e squared d c squared in the limit as the degree n of the polynomial tends to infinity. Okay? So although I call this operator the heat operator, it's not the usual heat operator that you see. Because first of all, I have a minus sign here. Usually you don't have a minus sign. And I have so the d by dc here is the complex derivative. Here you usually take the Laplacian. So the reason that I consider this operator is that the polynomial that I will consider today are all holomorphic polynomials. So if you consider the Laplacian instead of the second order complex derivative, this operator is just the identity operator. Okay? So there are some results in this direction in the math literature. The Polya-Benz theorem tells you that, well, if your initial polynomial has real roots, all the roots are real, then the heat evolved polynomial also has real roots. Okay? Of course, they actually did not focus on the heat operator case. They study a more general differential operator. And what I'm going to tell you today is to answer this question for a large class of random polynomials with complex roots. So the first example is it's not random. It's just a I just consider the case of a monomial. So you apply the heat operator to a monomial. What you get is a scaled Hermite polynomial of degree n. So Hermite polynomial, I'm not going to write down the formula here. Hermite polynomial is sort of the very classical orthogonal polynomial. So if you know Gaussian distribution, Hermite polynomials are the orthogonal polynomials of the Gaussian distribution. So the degree n here corresponds to the degree of the monomial. Okay, and this t over n here goes to the scaling. So although I don't show you the formula of a Hermite polynomial, I'll show you the plot of the heat evolved monomial, which is the scaled Hermite polynomial. So I need to somehow normalize by e to the minus x squared over 2, which is somehow a scaling of the Gaussian density. Otherwise, because if I simply plot the Hermite polynomial, it just grows too fast. We don't see any behavior. Okay, so I multiply by the Gaussian with t equal to 1, and this is the picture. You can see that the roots are pretty close here between -2 and 2. Okay, and now my question is, what is the root distribution? So the answer, this is a classical result, a very classical result. The root distribution of a Hermite polynomial is approximately the semicircle law on the interval minus 2 square root t to 2 square root t. Okay? So here is a histogram of the roots of the heat-evolved monomial at t equal to 1, and I plot that with the semicircular density. So you can see that the histogram here fits the density pretty well. So the second example that I'm going to tell you, you see that I have a quote here, because the conclusion of the example that I'm going to tell you here is actually a conjecture. It is not a proved theorem. Okay? So I consider a random matrix C with independent complex Gaussian entries with mean 0 and variance 1 over n. Okay? So it's a random matrix. All the entries are independent and they all have the same distribution. And in this case, classical theory in random matrix tells us that the eigenvalues are approximately uniform on the unit disk. So here is a simulation of the random eigenvalues of a sample of these random matrix. So you see that the roots are approximately uniform on the disk. So what I'm going to show you this time is that, well, I have a random matrix C. So if I have a n by n random matrix, I can consider its characteristic polynomial, right? And the characteristic polynomial is of order n, and I can consider the heat evolution of the characteristic polynomial. Now I'm going to run an animation to show you the evolution of the roots of the heat evolved characteristic polynomial for t from 0 to 1. Okay? And we will see how the roots evolve. So let me stop for a while. So you see that, well, the roots initially distributed uniformly in the unit disk, and then it somehow deformed, stretched horizontally, and it becomes an ellipse. And the distribution of the roots on this ellipse is also uniform. Okay, so the ellipse is changing, but the distribution is uniform on these varying ellipses. And then, well, let's see what we will see later, after time 1. All right. At time 1, you see that, oh, well, all the roots go down to the real line, right? So there you can see, well, you can tell the roots are not exactly on the real line. You can see that the points are somehow off a little bit, because the degree here is not infinity. I have a finite degree polynomial here. Okay, but it's kind of convincing that if we take n to infinity, the roots will distribute on the real line at time equal to 1. Okay, and then the question is, well, previously, before time 1, the roots are uniformly distributed on an ellipse. And right now, what is the distribution? Well, the answer is in our conjecture, in my conjecture with Hall, that is on arXiv last year. So the limiting roots distribution of a heat evolved characteristic polynomial is uniform on the ellipse with semi-axis 1 plus t and 1 minus t for t less than 1. And for t bigger than or equal to 1, the limiting distribution is the semicircular distribution on the interval minus 2 square root t to 2 square root t. So the last example of this heat evolution polynomial is actually an example that we saw a few minutes ago. I consider the wild polynomial. Okay, so let me recall that the wild polynomial has this form: the sum of ck square root n c to the power k divided by square root k factorial. Okay. Now the limiting root distribution is uniform on the unit disk. Okay. Well, there are more outliers than the random matrix if you are questioning whether that's true. That's true, but that's not the main topic of today. So by the main results of today's talk, the limiting root distribution of the heat evolved Weyl polynomial is uniform on the ellipse with semi-axis 1 plus t and 1 minus t for t less than 1. So here I plot a simulation with t equal to 1/2. So you can, with the ellipse, okay? You see that the roots are pretty uniform in the ellipse. And at t equal to 1, I plot a histogram of the real part of the roots. So this is similar to the random matrix case. The roots are not exactly on the real line. They are very close. So I take the real part, so I can plot a histogram. So and I plot the semicircular density. You see that the histogram follows the semicircular density. There are some outliers here, all right, but in terms of the bulk distribution, they agree. And this is a rigorous result in contrast to the conjecture in the previous example. So,
John, may I ask you a trivial question? You can mention that there's a special function Hermite polynomial behind your theorem. How about this one?
There are also Hermite polynomials involved because because his operator is linear, and I have a sum of linear combination of some monomials, right? So if you apply the heat operator, it's a linear combination of Hermite polynomial. Yes. So that explains why actually, and I will actually show you the formula later in the talk. So I'm going to tell you the set of the main results today, which means the random polynomials, the class of the random polynomials that I will look at today. So the random polynomials that I look at today all have rotationally invariant distributions of zeros. And it's actually more technical than that. So these class of polynomials were first considered by Kabruchko and Zaporozhai. Okay? So they have this form. It's a sum of ck times akn times c to the n, where ck are IID complex valued random variables with finite log moment, and akn are deterministic coefficients that can be somehow understood in the limit as n to infinity. And how do I understand that? I want to use a so-called exponential profile to understand that. And for exponential profile, I mean a concave function, concave continuous function. More precisely, I mean absolute akn is approximately e to the n times gk over n. So let me give you some examples. The first example is the Weyl polynomial that we have already seen 2 times in my talk. This is the third time that I'm giving it as an example. So this is the Weyl polynomial. Is the sum of ck times square root n c to the power k divided by square root k factorial. So the exponential profile of this polynomial is given by negative 1/2 times alpha log alpha minus alpha. Okay. Well, to compute the exponential profile is you only use the Stirling formula. You just apply the Stirling formula to the k factorial, and then you will get the exponential profile by some straightforward calculation. The second example is actually a generalization of Wild polynomial. So here, well, this is the formula of Wild polynomial. What I changed here is that the square root here of the n and the square root of k factorial, I changed that to other power. So this polynomial is called the Littlewood Offworth polynomial. It has a parameter beta, and is given by this form. Okay, so the n is now raised by the power beta, and k factorial is raised to the power beta. So do you have do you have another laser pointer? Because somehow mine is not working very well. All right. So so the exponential profile of the Littlewood Offworth polynomial is given by negative beta times alpha log alpha minus alpha. Okay. Again, you just apply Stirling formula to the deterministic coefficient, and you will get the exponential profile. All right. So why do I need that kind of assumption? So let me recall that with a random polynomial, what I'm interested in is the distribution of the roots. And in particular, I'm looking at the limiting root distribution. All right, so I fix the degree n, I look at the roots, and then I take the n to infinity and try to see the limiting root distribution. Okay, so here is an observation. With a Kabrishko-Saporosas polynomial, the polynomial is a sum of independent random variables. Right? You fix any c, the independence come from ck. So you are summing over n plus 1 independent random variables. And this property is actually very important. We can use this property to perform a lot of analysis. And the first thing, or what is relevant to my talk, is that the magnitude of Pn is dominated by the largest term among these n plus 1 term. You will ask, hey, you just told me we are interested in the root distribution. Why are you telling me the magnitude of the polynomial? I will tell you the answer in 2 slides. Okay, so the magnitude of Pn of the polynomial is dominated by the largest term. Okay, so what I mean is that you fix a c, a complex number c. The magnitude is dominated by the largest term, which means we can just find the largest term in the sum that has the largest magnitude. Okay, so let's go ahead and compute the largest term in magnitude of Pn. So Pn has this form, where Akn can be approximated very well by e to the n times g of k of n. Okay, where g is the concave exponential profile. And then now I do a change of variable. I write k to be a fraction of k. And well, to compute the largest term in magnitude is the same as computing the largest term among 1 over n log of the absolute value of this deterministic term. Okay? So you may ask why I'm excluding the ck, because they are random. We just treat them, well, they are the same. We cannot, I don't throw that into this analysis because we just assume they are the same because they are identically distributed and they're independent. So this g gives you g alpha here, and then c to the k gives you alpha times log absolute c. Okay? And well, I want to find the largest term in magnitude of Pn, meaning that I just find the largest alpha that maximizes g alpha plus alpha log absolute c. And why do I want to consider the maximum of this function? Because that actually determines the limiting root distribution. As in this theorem. This theorem is by Karbushko and Staporosas in 2014. So the limiting root distribution of Pn is a rotationally invariant compactly supported probability measure that I call that nu naught. And this measure is determined by the log potential, which is given by this form. You just integrate the measure with log of absolute C minus W. And the log potential is computed by the method that I call the largest term width. Okay? So you have a term of n plus 1 terms, you have a sum of n plus 1 terms, you just find the largest. So that's what I call the largest term width. So previously, I have all of these terms, like after I take 1 over n log. Okay? So I just find the supremum of this. And that gives you the log potential of the limiting root distribution. Okay? Well, you can see that I somehow exclude 0 here, because if you put 0, the log becomes minus infinity. But that actually, well, missing one point, it doesn't matter. You can still compute the measure with the log potential missing just one point. Namely, you take the Laplacian to the log potential. Okay? All right. So what I'm interested in today is the heat flow of random polynomials. Actually, I'm going to consider the heat flow of Karbushko and Saporosas polynomials. So suppose that Pn is a Karbushko-Saporosas polynomial. That means the AKN here can be understood by a nice exponential profile G. Okay. Now, if you apply the heat operator, let me recall that this is our heat operator with the complex derivative here. If you apply the heat operator to Pn, because the heat operator is linear, it's the same as, well, you are summing up Ck, Akn times the heat operator applied to the monomial. So in one of the earliest example of my talk, I told you the heat operator applied to the monomial is a scaled Hermite polynomial. So this is a scaled Hermite polynomial. So if you apply the heat operator to degree k monomial, you get a degree k Hermite polynomial. And the scaling involves a dilation. So inside the Hermite polynomial is scaled by square root n over t. That comes from the t over n here. And then you also multiply to the Hermite polynomial by an overall factor, t over n to the k over 2. Okay? And now I'm interested in the limiting root distribution of this polynomial. So if you observe this sum, it is again a random sum of n plus 1 independent random variables, right? Because the Ck here are independent. It's just, well, what I have here is much more complicated. In the Karbushko and Saporosas case, this is much more clean. And right now, we need to understand the Hermite polynomial. Otherwise, we are in the same situation as before. Okay. So, well, because we're in the same situation, the limiting root distribution of the heat-evolved Karbushko-Saporosas polynomial is given by the same method, namely the largest term width. You just look at all the terms here and find the largest term, and then determine the log potential. So let's compute the largest term here. So again, I will compute 1 over n log of the absolute value of this deterministic part. Okay. So again, the largest term dominates the magnitude of heat-evolved polynomial. This is just like this is what the largest term wins method is doing. So we have the estimate here. Well, again, we write k as a fraction of n. and we compute 1 over n log of absolute value of the deterministic part. So this is the term in the sum of heat evolved polynomial without the random variable ck. And the akn here gives you g alpha because g alpha is the exponential profile. It describes the coefficient akn nicely in the limit. And well, the middle term here comes from the t over n to the power k over 2. You need to split this term into 2 factors, and 1 factor goes to this term. And then you group the other factor to the Hermitian polynomial, and that gives you this mysterious function that I use psi to denote. It's alpha times psi of c over square root t alpha. What is psi? Psi is the log potential of the semicircular law on minus 2 to 2. Okay? So I'm not going to write down an explicit formula of the log potential. All I want to tell you is that, well, the semicircular law comes into the picture because in one of the earlier examples, I showed you the root distribution of the Hermitian polynomial converges to the semicircular law. Okay, so this is somehow how it is coming. Okay, and then I use the largest term width method to compute the limiting root distribution of this heat evolved Kaprushko-Sapir-Whorf polynomial. Namely, I just compute the supremum of this term over alpha from 0 to 1. Okay, so the limiting root distribution here is no longer rotationally invariant, but it is still compactly supported probability measure. And the log potential is given by the supremum of the function that we calculated in the previous slide. Okay. So here is an old example that I showed you already the second time. So if you consider the case of wild polynomial, sorry, I'm missing a square root n here actually. But well, let's say we consider the scaled wild polynomial, then the roots of the heat evolved wild polynomial at t less than 1 is uniform on the ellipse. Here I'm showing you an example with t equal to 1/2. And at t equal to 1 is semicircular, that you can compute that using the formula in the previous slide. So in semicircular, so the other example is the Littlewood-Orford polynomial that I also gave an example previously. Is an example of the Kaprushko-Sapir-Whorf polynomial. So here, so this is the Littlewood-Orford polynomial, and I take beta equal to 0.3. What I'm going to do is that I'm going to run a simulation of the roots of the heat evolution of this random polynomial for time from 0 to e to the 0.4. So let's start. All right. So I've run that for just a short time. You see that the roots kind of deform nicely and smoothly. Again, it changes from distributing on the disk to an ellipse. And you see that, well, it's very smooth. There is no singularity. It looks like it has a nice density in the ellipse. Well, let's see what we will see if we run time a little bit forward. So at this time, you see that, well, clearly, there are two curves of singularities formed. Okay, you can see that there are two curves here that the roots are lining up here. Clearly, that's a singularity. It's a singular part in the two-dimensional Lebesgue measure. So let's see what we will get if we run time forward. So what we saw is that, well, the singular parts evolve, right? So it becomes it's like collapsing and collapsing, getting closer and closer to the real axis, and at the end, at t equal to e to the 0.4, the roots are on the real line. Well, again, approximately on the real line because n is just 1,000 here. And there is one outlier here, but that doesn't change the Liberty work distribution. And now, if I let you guess the distribution of the roots on the real line, what would you get? Well, it will be our favorite semicircular law. So here I'm plotting the roots on the complex plane at t equal to e to the 0.4. You can see that the roots are definitely not exactly on the real line, but they are close. So in the limit n to infinity, they will actually be on the real line. And here I plot the real part of the roots, and they follow the semicircular density. Okay. So let me summarize what we observed in the animation.
No, tomorrow I have a silly question again. So the picture you show us, the density is not so uniform, right?
Which density?
Can you
You mean the animation?
see in the middle? The density is certainly
Right,
small.
right.
Small.
Well, when beta is not, well, I mean for general beta, this is not uniform on the disk. Actually, for smaller beta, the roots are like pushing to the unit circle.
Within the
and-
boundary.
Right. And for bigger beta, it's like the roots are pushing to the origin. And when beta is 1/2, it's the uniform distribution on the unit disk. Right. And this is, well, yeah, this is why I pick betas less than 1/2 and show you the singular part. So what did we learn from the animation? So there is one critical time. Since then, we see two singular curves. Okay, so we summarize that where there is one time, a critical time, that we see singularities. It may not be two singular curves, but we will see some singularities. Okay, and the singularities, the singular part actually evolves. It's not the same singularity part over time. And then, at some point, all the roots collapse to the real line, and they form the semicircular distribution. And what I emphasize is that they are exactly semicircular distribution on the interval minus 2 square root t to 2 square root t if you let n to infinity. Okay? And this is actually in our theorem. In my theorem with Hall, Karpushko, and Yaloui. Well, we actually need some minor technical assumptions to the exponential profile G that describes the deterministic coefficients. But other than that, these two critical times can be computed explicitly using the exponential profile G. Okay, and well, so the theorem just confirms our observation. When t is less than t sin, so this is the first critical time where the singularities are developed. Before that, the distribution has a bounded density. At t bigger than, well, when t is bigger than t sin, you will see some singularities in the distribution. And then the singularities evolve up to another critical time, TSC. Well, SC stands for semicircular. So there is also another critical time, TSC. After TSC, the distribution becomes exactly equal to the semicircular distribution on the interval minus 2 square root t to 2 square root t.
Do you know these two numbers precisely?
Which two? In some cases, yes. So in the Littlewood Offworld polynomial, TSC is e to the 1 minus 2 beta. T sin is beta over 1 up. beta over 1 minus beta. In some explicit case, we can actually compute that. We have a closed formula.
How do you write that?
It's, well, T sing is something like the infimum of some expression involving the second derivative of G and something. TSC is exponential of something involving G. Yeah, it's not a very nice formula, but it's an explicit formula that I don't have it on top of my head.
Yeah, so what property changed which lead to these kind of situation?
So what do you have? Which property?
At these particular T,
Oh.
what property changed?
So, it's
there
about-
different behavior.
It's about regularity. Before T-sing, the density is bounded, except some boundary, the density is actually pretty nice. And then at T-sing, you will see some singular curve or singular part of the distribution. And at the last critical time, it's just the semicircular distribution.
Yeah, but you already said this. But my question is, which property would lead to this kind of three different situations?
Is the largest. So remember the log potential is determined by the largest term wins method, right? So there is some alpha. So let me go back to the animation. So when I click the run button, you see that the roots somehow deform, right? And it's somehow compressed here. So in this particular case, the singular curve formed when the roots in the upper part runs faster than the lower part. So they kind of stick together. So you see a singular curve in this case. So in general, it all comes from the log potential. So the last property that I want to tell you about the heat evolution is the push-forward property. So let me recall that. Before T-sing, the distribution of the root is very nice. You have a nice density, and in the simulation you see that the roots kind of evolve smoothly, right? So the push-forward property is to understand this behavior, right? So under the technical assumptions, which means we can determine the T-sing, we can find a map that we actually call it the transport map, TT on the compressed plane. This map is very nice. Let me tell you the very nice properties of the map. The first property is that the TT is bijective from the compressed plane to the compressed plane. And the second thing that makes it very canonical, very natural, is that it maps circles centered at the origin to a boundary of ellipses. Okay? And the third point is that if you fix a point W on the compressed plane and let T go from 0 to T-sing, TTW is linear in T. Okay, so I will give you an example of TT later in 2 slides with the wild polynomial. But I just give you a sense that it's a very nice map. And the conclusion of the theorem is that the limiting root distribution of the heat evolved polynomial is the push forward of the limiting root distribution of the original polynomial by TT. Namely, while you have n roots of this Kapluchko Saporosas polynomial, you just take each of them by TT. What you get is approximately the roots of the heat evolved polynomials. So how do we interpret that? Well, we call that TT is linear in T, which is actually, I would say, one of the most interesting and important property of TT. So what the theorem suggests is that the individual zero of the random polynomial evolve along curves given by TT. That means if you start with a root, the trajectory of this particular root is TT of W. Okay? So because TT of W is linear in T, we expect zeros to evolve in straight lines with constant velocity because it's linear in T. Well, we didn't prove that. We didn't prove such a strong statement. And the theorem tells us that the bulk evolution of the zeros is consistent with this motion of individual zeros. Okay. And this is actually our conjecture that the roots are evolving along those curves. So let me give you an example. That is our favorite wild polynomial. Okay. So the TT map here is very simple. It's given by W plus T times W bar. Okay. So the velocity is W bar. It depends on the initial root. Okay. And in this case, T thing is 1. Okay. I just tell you this fact. So what I'm going to show you is a simulation. Okay. So the blue dots are the roots of the wild polynomial. I'm just running the simulation with n equal to 100. Okay. So the gray lines here are the trajectory of the initial root if they follow the trajectory given by TT of W. Okay, so the gray lines are the lines plotted using W plus T W bar. Okay, and we will see how close the roots evolve along this line. So they are not exactly on this line. I just tell you before I run the simulation, but you will see that they are very close. Okay, you see that the roots travel basically along the gray lines. Of course, it's not exactly on the gray lines because n is just 100 in this animation. Especially the roots around the bottom, the roots don't even get to the other end of the gray lines. But it's pretty convincing that we should interpret the push-forward theorem as the motion of the roots. That's why we call the TT map transport map. So here is a PDE perspective of the push-forward theorem. The logarithmic potential of the limiting root distribution satisfy a Hamilton-Jacobi PDE given by dut dt is equal to -2, the real part of dut d in c squared. Okay? And what is the TT map? The TT map is related to the characteristic curve CT with initial condition C0 by TT of C0 is CT. That means the push-forward theorem suggests the roots are evolving along the characteristic curves of the log potential of the limiting root distribution. Okay, so as you can see in my talk, there are a lot of open questions, a lot of interesting questions. So we can further study the singular part of the heat-evolved Littlewood Orford polynomial or some other quadruple sub-Rosas polynomials. And we also do not need to limit ourselves to the heat operator. We can study some other operator. So this is a picture of the Cart polynomial, which is actually a Littlewood Orford polynomial at t equal to 0.6. It's a very, very nice. It has very nice structure. We actually have some conjectures and observation how the roots evolve, and I hope we can write a paper and tell you how they actually evolve. So, the semicircular distribution marks the end or the completion of the evolution of collapsing all the complex roots to the real line. And this semicircular histogram also marks the end of my talk. Thank you for your attention.
Let's thank the speaker. So, any comments or questions?
Can we go back to the example? The roots are not uniform distribution in the disk. Yeah, thank you. My question is, when T goes, the roots are collapsed and form the two curves. Why we call the two curves are the singularities?
Because, well, okay. So before the two curves form, in the limits, you can describe the distribution of the roots by a nice density. Density with respect to the Lebesgue measure. Does that make sense? And then, when singularities form, what I mean by singularities here is that, well, you cannot describe the distribution of these zeros by a density function on R2. Yeah, that's why I mean singularities, because it's a singular part, of course, with respect to the Lebesgue decomposition with the Lebesgue measure.
So the singularity only appears when n goes to infinity or finite?
Infinity. Like for finite n, all of these are singular because we only have n points. So it's actually an atomic discrete measure. But what I'm saying is as n to infinity.
And also the exponential profile you define, it looks like some kind of alpha log alpha. Is that related to some kind of entropy or something?
Sorry? Next.
Yeah, alpha is in 0 to 1.
Right.
Is it some kind of entropy or something?
That's a good question. So you can it's kind of a log potential, right? So it's kind of a log potential here, the G alpha. Except well, you need an extra term because that's the C to the K. But yeah, that's entropy. I'm not sure, but it's the somehow potential. It's the potential that describes the coefficients.
So there was a question asked in the very beginning, why different polynomials behave so different?
So it comes from the density of the original, the initial polynomial. Like right now you can see that the roots are denser outside. So the singularity formed outside. So if you, for example, I can give you another example. If beta is bigger than 1/2, the roots are more dense around the origin, and the singular curve formed on the real line. So it comes from the difference of the density of the roots, and when they evolve, the roots actually satisfy a system of ODE, and somehow the roots some roots just go faster than the other, and then they just push together.
We know. So if you are given a polynomial, if you are presented a polynomial, can you say whether it will more or less behave like a vowel polynomial or like little word Alford polynomial? So that's the question.
Yes.
Yeah,
Well,
that's
yes.
the
So
question.
first, the initial polynomial that I consider have rotationally invariant roots. So well, I can only tell you if it's more dense outside, it's like the Littlewood Alford case. If it's more dense inside, singularities formed on the real line. But if you have very dramatic changes of density, like you have high density, low density, high density, low density, then
But you have to answer from the polynomial.
well, well, from the point then it's given by the exponential profile of the polynomial. It's determined by the log potential. Yeah, you just compute, well, for each C, you compute the supremum of this, right? And then the singularity comes from, well, roughly speaking, for nice enough example, it comes from when the log potential is not differentiable at that point. Somehow, something strange would behave here. Maybe like there are two alphas that make the maximum. Like yes, there are some ways that you can actually calculate the singularity curves, and in this future developments picture, we actually have a formula to describe these density curves kind of explicitly. Well, of course, also the same in the Littlewood Alford. I don't have to show the Cots case. Like in this Littlewood Alford case, we can actually compute an equation of these two curves explicitly using the log potential. Just see whether there are two alphas that give the maximum, or whether the log potential is not differentiable at that point.
So any of these kind of result, I mean, beyond the model context, I mean, let's say for PRD field, do we have this kind of things?
No, not sure. That's probably too, yeah, most of the yeah, not sure.
Okay, so let's thank John Wei. Oh, sorry.
Thank you, Taiwan. As you know that there's another important distribution in random matrix, which is Marchenko-Pascal law. So if I consider the characteristic polynomial of convex matrix, can I expect similar things to happen?
Yes. So this is actually the ongoing work. The second point that I say here, the Marchenko plus 2 corresponds to another differential operator, and there is a family of non-Hermitian Marchenko plus 2 distribution. It is given by product of two rectangular random matrices. So when the parameter changes, the correlation of the two random matrices change, and yeah, and gives you different limiting eigenvalue distribution. And yes, that we can study that using this technique.
So any other questions?
I'm just curious about why we consider key operators here.
So heat operator. So well, my story is actually this example, like what I put in quote. So in this conjecture that Hall and I put on the archive last year, we found that well, we actually used some heat kernel analysis that apply to this particular random matrix, and we found that well, we can kind of deform the distribution of the roots using the heat operator. That's why I'm interested in this problem. And actually, like on this slide, I kind of told you, but polynomial bands actually did not limit their theorem to the heat operator case. They consider more general differential operator applied to polynomials.
Okay, so any other questions? So if there's no further questions, let's thank Ching again for his wonderful talk.